So I wanted to do a couple of these, at least one, maybe two of these with you from this worksheet packet, just to make sure that you're doing the right thing. If you have any questions, please let me know, and I can try and help you before we get back to school. So 1 and 2 on the front side have to do with approximating the rate law for the reaction using the steps. Okay. And so we have to, the steady state approximation just means that we're going to have to substitute in for these reactions to derive the rate law for the overall thing. Okay. So step 1 is a fast reversible rate law, which is important because that double-sided arrow means that that gives us actually 2 rate laws in one. And then step 2 is a slow rate law that's only in the forward direction. So there would only be 1 rate law for that step. And since it's slow, then that means that that is the rate determining step. Okay. So that's the one that's going to help us get the overall rate law for the reaction. So first thing, step 1 has 2 reactions going on. So with step 1, the forward reaction, remember we only use reactants. So the forward reaction, the rate law for that would be rate is equal to K constant. And I'm going to put a 1 here just so that we know it's from step 1. And it's the concentration of I2. And since there's no coefficient there, we would say that it's to the first power. We would guess. Okay. Now for step 2, or sorry, step 1, the reverse reaction. This is going the other way when I2 is the reactant and 2I, or no, sorry, 2I is the reactant. I messed that up. And we're going that way. The rate would be equal to K, and then just to show that it's the reverse reaction from step 1, you could label that as -1. So negative would mean reverse, times the I, and since it has a coefficient of 2, you would raise it to the second order. Okay, so those are both the rate laws for those 2 steps, like the 2 parts of step 1. So then in step 2, there's only 1, which is nice. And so the step 2 rate law in the forward direction would be rate is equal to K, and I'm just labeling it K2 so that we know it's from step 2, times the concentration of H2 times I to the second order. Okay, now the reason why we can't just use the rate law from step 2 to be the overall rate law is because it involves the intermediate. The I by itself is an intermediate because that would cancel out if you added them together. So we have to replace this part of the step 2 rate law so that we can then get the overall rate law without intermediates involved for it. Okay, so the way that we're going to do that, we have to do some work with the step 1 reaction, forward and reverse rates. Okay, so now with that, since it's a fast reversible rate, what that means is the rates of the forward and the reverse reaction are equal to each other. So if these 2 rates are equal to each other, that means that we can set the other side of the rate laws equal to each other. So from the forward reaction, the K1 times the concentration of I2 would be equal to the K -1 times I squared. Okay, now the rate law constants, the Ks, in our purposes, we just get rid of them. We don't have to worry about them because it all just combines to make a new rate law constant in the end. So by doing that, then that means that the concentration of I2 is equal to the concentration of I squared. Okay, or I to the second order. So this right here will help us replace this part right here in the step 2 rate law, so that we can then get the overall rate law for the reaction, where it says the I2, we're going to replace that with just the I squared replaces with the I2. Okay. This is all getting confusing. Sorry. So rate is equal to K. And now I'm not going to put a little subscript on this K because it's just the overall rate law. It's not for one specific step. Times, we have to keep the H2 as part of it. But then instead of the I squared, we put I2 from over here, replace 10. Okay, so that is how you do that. You're just replacing, subbing in something that is equal to that intermediate to make it work out. So number 2, it's a multiple choice problem, but you do need to still do all the work so you know which choice would be the correct, because it does say show your work for proof. So I want you to try that. This one, we have 3 steps. Notice how in this first step, so if this is 1, 2, and 3, in the first step, it is reversible. So that means step 1 is going to have 2 rate laws, one for the forward reaction and one for the reverse reaction. So be careful there. Okay. Now, drawing a energy diagram or energy profile diagram. Let's skip to number 4. So we want to draw an energy profile for a reaction involving a single intermediate and explain its features. How do we know that we're able to detect the presence of an intermediate in the reaction mixture, however short-lived it might be? So the main thing, so this part is supposed to be the reactants. Okay, so I'm just getting it started for you. So when we look at energy diagrams or energy profiles, we know that there is a presence of an intermediate when there is a dip, when there are multiple humps in the graph. Okay, so don't draw this, but if it was just like this, then that means that there is no intermediate because there is only one hump. Okay, so that's what it looks like when there's no intermediates. Now, delete all that. If there isn't an intermediate, we have to have a dip. Every time there's a dip, that equals an intermediate. So since we just have one single intermediate, that means that we're just going to have one dip in our reaction. And so when we have our 2 humps, the humps should not be the same height. One of them will be for the rate determining step and one of them won't be. So the way that I did it is I made my first hump taller than my second hump, like so. Okay, so this right here tells us that that is the intermediate. We have one intermediate in our profile for the reaction. Okay, so why is it possible to answer that question? It's possible because there are 2 humps in the graph. It exists as its own unique species because there would be a second activation energy requirement in order for the intermediate to be taken care of in the reaction. So, you know, this height would be activation energy for the first step, and then this would be the activation energy for the second step. So that's what I was talking about there, that each hump in the graph takes its own amount of energy to overcome in order to make changes. And so once the intermediate has been formed, then you cannot get rid of that intermediate until enough energy is placed in there. Okay, so hopefully number 5, you have to draw your own graph. So I want you to try that yourself. And we'll talk more about this stuff later. So you should finish up the notes for today, and that will help with the last 2 questions in the packet. And we'll talk more about this later.